Hello everyone. Today I will be explaining the topic extension of Turing machine, which is a part of theory of computation. This presentation is prepared by me, Radhika Patil, under the guidance of Professor Hemavati Biradar. Let's get started. In this slide, we start by understanding why we even need extensions to the basic Turing machine. Turing machines are powerful models of computation, but sometimes to make tasks easier or faster, we use extended versions like multi-tape Turing machines or non-deterministic Turing machines and more. But remember, all these extensions do not increase the power of TM. They only make programming simpler or faster. In this lesson, we will cover multi-tape Turing machines, equivalence of one-tape and multi-tape Turing machines, a reminder about fitness, running time and many tapes to one construction, non-deterministic Turing machines, simulation of NTM by DTM. Let's begin with the multi-tape Turing machine. A multi-tape Turing machine is just like a normal TM but with a multiple tapes instead of one. It has a finite control. Several tapes divided into cells. One read or write tape and one initial state and one or more accepting states. How does it start? The entire input is placed on tape 1 and all other tapes initially contain only blanks. So the control starts in the initial state and other heads can be anywhere since their tapes are blank. Multi-tape machines help us do parallel like operations, making computations faster. Now let's see how a multi-tape Turing machine performs a single move. During one move, the control enters a new state and it may stay the same or change. A symbol is written on each tape. The symbol may change or remain the same. Each tape head moves independently, can move left, right, or stay. So, the overall multi-tape Turing machines are just more convenient versions of single-tape Turing machines. On this slide, we can see figure 8.16. It shows multiple tapes placed horizontally and with a single control unit above them. Each tape has its own head and all heads read simultaneously. This clearly demonstrates how multi-tape machines simulate parallel memory, making them more flexible and efficient in layout. Here comes an important theorem. So, every language accepted by multi-tape Turing machine is accepted by single-tape Turing machine. This means multi-tape machine do not increase power. So the idea of proof. A one-tape Turing machine simulates multiple tapes by dividing the tape into tracks. Each track stores one tape's content and markers indicates tape head positions. The simulation process. Visit each marker, reads symbols, compute next state, update symbols and move markers. So multi-tape Turing machines give only convenience, not additional capabilities. This slide shows how one tape Turing machine simulates a two-tape Turing machine. You can see multiple rows representing tracks and each track contains a symbol with the head markers shown as X. This is how multiple tapes are compressed into one tape. So some students are wonder, why can't we store head positions inside the finite control? The reason is simple. To store any positions, we would need infinite steps. But Turing machine must always have a finite number of states. So tape head position cannot be stored in the control. Instead, they are stored on the tape itself using markers. This maintains the fundamental Turing machine principle. Finite control and infinite tape. When one tape Turing machine simulates a multi-tape Turing machine, it becomes slower. So the important theorem is here: simulating n steps or k steps. A multi-tape Turing machine takes big O of n square time on a single tape Turing machine. But why? Head markers may move apart and need long scans. Each simulated step by step may take big O of n time. For n moves, it takes total time n into n, that is big O of n square. Even though it is slower, both machines are polynomially equivalent, and meaning they run in a comparable complexity classes. Now let's understand non-deterministic Turing machine. A non-deterministic Turing machine has a multiple possible moves, but a deterministic Turing machine has exactly one possible move. The transition function returns multiple next states. This means the machine branches into many possible computations. So the acceptance rules, and if any branch reaches an accepting state, the NTM accepts. Although NTMs may run faster, they do not recognize more languages than DTMs. The DTM's process. Tape 1 stores a list of IDs, instantaneous descriptions. Each ID represents a branch. The machine uses BFS, breadth first search, and if any path reaches accept state, the DTM accepts. So NTMs are powerful for design but do not increase computational capability. Let's quickly see the steps. Examine the current ID. If it is accepting, accept. Otherwise, generate all possible successor IDs. Add them to the queue. Move to the next ID. So, if NTM accept by any path, the DTM will eventually discover it. To summarize the entire topic, multi-tape Turing machines improve efficiency, not the power. One-tape Turing machine and the multi-tape machines accept the same languages. Tape positions cannot be stored in the finite control. One tape simulation is slower, that is big O of n square. NTMs allow multi-tape possible moves. DTMs can simulate NTMs using BFS. And all extension improve convenience, not capabilities. So the standard Turing machine remains the fundamental model of computation. Thank you so much for watching this video.